All right, so continuing this proof, it gets a little tricky here because we have to take the x derivative of all this. Now we have to remember what n is. N, I'm going to write this over here, n is a function of x, y, and z. But z is a function of x and y. So if we want to take the x derivative of n, it's going to be dn dx plus dn dz dz dx. We have to apply a chain rule. Okay? I'm going to start all the way back here because I'm going to need some space. So the x derivative of n is dn dx plus dn dz dz dx. dn dz dz dx. Okay. Plus, okay, now we need the x derivative of this quantity. And we're going to need a product rule. Okay, again, p is a function of x and y and z. Z is a function of x and y. Okay, so I'm going to take the derivative of the first times the second plus the first times the derivative of the second. Okay, so I need the x derivative of p, which is dp dx plus dp dz dz dx. So it's d times dz dy, and then plus the first times the derivative of the second. So p times the x derivative of this. So that's going to be the second derivative of z with respect to x with respect to y. Okay. Now I need to do this. Minus, now I need the y derivative of m. And again, m is also a function of x, y, and z. Z is a function of x and y. So the y derivative of m is the m dy plus the m dz dz dy. Okay, so I'm just going to take that minus out of the entire thing. So dm dy plus dm dz dz dy. Okay, plus, and I've got another product rule. So I'm going to take the derivative of p, derivative of this times this, and then plus this times the derivative of this. My product rule. Okay, so I've got dp dy plus dp dz dz dy. Okay, so all of that times dz dx. And then I've got plus p times the y derivative of dz dx. So that's going to be d squared z dy dx. Okay, and all of this is going to be times dA. Okay, so let's simplify. So I've got double integral. I've got dn dx. Actually, I'm going to write that as the x partial of n, okay, plus the n dz, dz dx. So that's going to be the z partial, dz dx. Okay, now I've got dp dx, dy dz. So I'm going to say plus dp dx, sorry, did I say dz dy, dz dy, plus, now I've got dp dz, dz dx, dz dx, dz dy. Okay, and then plus p d squared z dx dy. Okay, minus dm dy minus dm dz dz dy. Okay, minus dp dy dz dx minus dp dz dz dy dz dx, and then minus p d squared z over over dy dx. All this times your dA. Okay, and there's some things that cancel here. So we've got the p d squared z dx dy minus p d squared z dx dy. Okay, the dp dz, dz dx, dz dy, and the minus dp dz, dz dy, dz dx, those go away. So what's left is the double integral of nx plus ny dz dx plus dp dx dz dy minus mdy minus mdz dz dy minus dp dy dz dx, all times your dA. Okay, and let's compare this to what we just had on the other page. Okay, which was this right here. Maybe if I float this down, we can compare the two. Okay, so minus dp dy dz dx minus dp dy dz dx plus ndz dz dx plus I think this one right here should be a dndz right here. That comes from there. I just rewrote that on. So that matches. And then I've got minus dmdz dz dy minus dmdz dz dy plus dp dx dz dy. There's that. Plus dndx and plus dmdy. Boom. Okay, so we just proved this one came from the right side of the equation. This right here came from, oops, go all the way up here. This thing, which was the left side of the equation. Okay, so that is the math to prove it. And then I do encourage you to take a look at the visual, the video that I found that really kind of shows intuitively why this all